Okay, welcome back. And this is Thanksgiving week. So I first would like to wish happy Thanksgiving to everyone. And today we have speaker from Caltech, Shreyas Vissapragada. He's from Caltech 50 year, working with Heather Knudsen. And Shreyas is in job market this year. So I wish you good luck. So today he will talk about the evaporating atmospheres of exoplanet. So the floor is yours, Shreyas.
Thank you so much for the kind introduction, Serena. And I'll just quickly mention, I will take a couple of breaks in the middle of the talk. So in case anyone has any burning questions they'd like to ask, there will be spots throughout.
And before your talk, I'm sorry, I would like to remind everyone. So there are people with a very low internet speed. So if you could turn off your video, that would be great. Thank you. Okay, go ahead. Sorry about that.
No problem. Yeah, so like Serena said, my name is Shreyas. I am a fifth-year PhD student in the Planetary Science Department at Caltech, where I work with Professor Heather Knudsen. And today I'm going to be talking about some of my thesis research, which has been focused on studying the evaporating atmospheres of exoplanets, primarily using the metastable helium line, which I will go into in a bit. So to begin, I'll just kind of give a broad brush introduction to exoplanet atmospheric escape, just so everyone is kind of on the same page. I'll then talk about some instrumentation, some observations, and some theory that I've worked on, all in support of this problem. And finally, I'll mention a couple of future directions in which I'm really excited to take this work over the next few years. So we know of a lot of exoplanets now. So over 4,000 known exoplanets that have been discovered to date, and with the continuing success of missions like the Transiting Exoplanet Survey Satellite, or TESS, the number is only growing, and it's growing quickly. A subset of those 4,000 planets are plotted here in this really nice figure from the NASA Exoplanet Archive, a subset with measured masses and orbital periods. The detection techniques are noted with the symbols, but I'm not going to go too deeply into each of them in this talk, although I will mention the transit technique later. But one thing that really strikes me about this plot, the exoplanet mass period plane, is that it's not uniformly populated, right? There are some regions in the mass period plane where planets appear to be more likely to live, and some places where they're less likely to live. Now, some of this is a detection effect. For instance, it's quite difficult to detect a planet at a 100-year orbital period if your transit mission has only been going on for a few years. But that said, some of these over and under densities are real. And when they're real, they can tell us something interesting about how planets form and evolve. So to motivate my work for today, I'm going to talk about just one of these interesting features in the mass period plane, which is zoomed in here in this plot from a paper by James Owen and Dong Lai in 2018. I'll note that the circles in this image indicate planets that transit, and squares indicate planets that do not. In the upper part of this plot live the hot Jupiters. These were among the first planets to be discovered. Their masses are similar to Jupiter's mass, but they're on exceptionally short period orbits, less than around a week or so. The lower part of this plot, we have the hot Earths, or if they're close enough to their stars, they're sometimes called ultra short period planets. And these are kind of the low mass analogs of the hot Jupiters. They have masses up to around 10 times the mass of the Earth, but are on similarly short period orbits, less than around 10 days or so. But between these two extremes, there appears to be a missing population of hot planets that are around the mass of Neptune. And just by looking at this plot, we can tell that this probably isn't a selection effect or some kind of detection bias. All else being equal, it's easier for the transit and radial velocity techniques to find bigger things and things that are closer to their host stars. So if we see hot Earths down at these low masses, and we see cooler Neptunes out at longer orbital periods, then we definitely should be seeing hot Neptunes if they exist. So that raises the question, where are they? What happened to them? This is sometimes referred to as the Neptune desert or the subjovian desert problem in the exoplanet literature. One explanation that's been put forth for this feature is called photoevaporation, and it takes advantage of the fact that these planets are located extremely close to their host stars, and as a result, they're constantly being bombarded with high energy radiation at the X-ray and extreme ultraviolet wavelength ranges, collectively referred to here as XUV. So what this XUV radiation can do is it can penetrate deep into the planetary atmosphere and generate heat by photoionizing species like hydrogen and helium. When the resultant thermal energy of the planetary envelope begins to overcome the gravitational potential well that it resides in, the planet's atmosphere can escape. And it does so at a rate, in this sort of simplistic picture, it loses mass at a rate that's directly proportional to the incident XUV luminosity, or XUV flux, excuse me. I will note, however, that this constant of proportionality, epsilon, which I'll return to in a bit, is quite poorly known from observations. We have some theoretical models that sort of predict what we sort of expect epsilon to be, but different models give different predictions for epsilon. And until we know kind of the ground truth for what this proportionality constant is, it's quite difficult to assess the degree to which photoevaporation plays a role in clearing the Neptune desert. So just to demonstrate what I mean in kind of a schematic sense, here I've redrawn the mass period plane. And remember, the hot Jupiters live at the top, the hot Earths live at the bottom, and the hot Neptunes occupy this missing pizza slice in the middle. Photoevaporation asks the question, well, what if at the time the protoplanetary disk dispersed, this mass period plane was more or less uniformly populated? But the hot Neptunes couldn't hold on to their atmospheres against the effects of photoevaporation and were thus removed from that position in the mass period plane. Either they ended up becoming hot Earths, or they encountered some subsequent catastrophic processing like Roche lobe overflow and were removed from the population entirely. But that's not the only explanation we have for this population. We can also imagine, what if these planets didn't form where we see them today and instead formed much further away, and they migrated to their current positions? Maybe there's something about that process of migration that naturally doesn't populate the Neptune desert to begin with. And indeed, this has been pointed out in the literature as well. In particular, the process of high eccentricity migration, coupled with subsequent tidal evolution in this sort of short period range, matches the upper boundary of the Neptune desert quite well, as is shown from this figure from Jim Zillen and Dong Lai's work. The underlying physics here, by the way, is interior to this green line. Planets undergoing high eccentricity migration have pericenter passages that are way too close to their host stars, and so they get tidally disrupted. But planets on the other side of this green line can survive the process. So we have a couple of competing hypotheses here. Was the Neptune desert cleared out by processes like photoevaporation? Or was it never populated to begin with, because perhaps these planets formed, or these planets arrived to their current locations by a high eccentricity migration? To answer this question, one of the things we really need to do is empirically benchmark our knowledge of photoevaporation, measure the mass loss rates of planets so that we can understand the underlying physics and use that knowledge to figure out how much of a role photoevaporation plays in clearing the Neptune desert. So how might we do that? How might we observe evaporation in action? Well, these planets are best observed in transit when they pass in front of their host stars and block out a little bit of their star's light. So when you measure the stellar light curve, its brightness as a function of time, you see these periodic dips in brightness that are referred to as a planetary transit. And these dips not only tell you that the planet is there, but it also tells you how big the planet is, because larger planets block out more light. So this is kind of the case at most normal wavelengths. But remember, when a planet's atmosphere is escaping, some of the light that makes it to your telescope from the star is being filtered through low-density tenuous gas in that escaping atmosphere. And if we could choose to observe at a wavelength where that low-density gas becomes opaque, then suddenly the planet would appear much larger to us, and it would appear much larger than it does at other wavelengths. And if we were to see that, we would be able to infer the presence of an outflow in action. This is precisely why the discovery of the planetary metastable helium line was so exciting in 2018. So in this plot from the discovery paper, Jess Spake, who is the person that discovered this line, was taking a spectrum of the planet WASP-107b, a gas giant planet, with the Hubble Space Telescope Wide Field Camera 3. By spectrum, what I mean is the transit depth, so how much light the planet blocks out from the star, as a function of wavelength. And for the most part, the spectrum of WASP-107b is pretty standard, pretty typical of a gas giant planet with little hints of water absorption in the spectrum. And it's well matched by this model that Jess has drawn here in purple. That is, except for this one point at 10,833 angstroms or 1083 nanometers. And that's precisely where a special state of helium called metastable helium absorbs light pretty strongly in this outflow. Now, the Hubble Space Telescope Wide Field Camera 3, which was used to make these measurements, doesn't have the greatest wavelength resolution. But the great thing about this wavelength, 1083 nanometers, is that the Earth's atmosphere is transmissive at this wavelength. So we can use high-resolution spectrographs on Earth to zoom in, so to speak, on the wavelength axis. And this is precisely what James Kirk and collaborators did in 2020. And they found out that at the core of the helium line, this planet, WASP-107b, blocks out 8% of its star's light in the helium line. So when you convert that to an altitude, this is probing the planetary thermosphere and parts of the exosphere. So in other words, it's probing parts of the atmosphere with densities that definitely cannot be explained by a hydrostatic model for the atmosphere. It has to be hydrodynamic. So the theory for this line was actually worked out way back in 2000 by Sarah Seeger and Dimitar Sasolov, but it was resuscitated by Antonia Klopchich and Chris Harada in 2018. And with Jess's sort of groundbreaking observations in 2018, a bunch more people have started looking at this line and trying to observe atmospheric escape in action. And one of the papers that I think really highlights the power of this line is a work by Megan Mansfield from 2018, where she sort of performed the same study using the Hubble Space Telescope Wide Field Camera 3, but for the planet HAT-P11b, which is more of a Neptune-sized planet, and observed the same signal. And here in this figure, I think it highlights really well what you can gain from making these helium measurements. So in each grid cell on this figure, each grid cell corresponds to a one-dimensional isothermal Parker wind model at a prescribed mass loss rate and thermosphere temperature. And Megan has computed, these models, computed the helium signals that would correspond to these models and compared them to her data. And even in a schematic sense, you can see that this green outflow is too small to match the data. The red outflow is about just right. And the gold outflow is a bit too large. So the helium signal is a quantitative and precise tracer of the mass loss rate in a way that we've never really had before. Tracers like Lyman alpha suffer from tracing too high up in the atmosphere, in the exosphere, where material is more or less unbound from the planet. So it's really hard to trace the kind of wind launching physics that we're trying to understand with mass loss studies. So when I read this set of papers in 2018, I got really excited about the potential of the helium line for measuring mass loss rates. And I worked on a new technique called diffuser-assisted helium photometry to make these observations at Palomar Observatory. But before I go into that, I'll take a brief pause and see if anyone has any quick questions that they'd like answered. If not, I can continue on. So at the time that these studies were coming out, I was working on a technique called diffuser-assisted photometry at Palomar Observatory, using an instrument called the Wide Field Infrared Camera, or WIRC. And we were able to achieve really good precision with ground-based instruments. And indeed, our precision was starting to rival that of space telescopes. So to highlight this, I'm showing here, I think, our best performance to date, which is for the star Kepler 289. I won't go too deep into the science case for this one, but it hosts 3 planets in a near resonant configuration. And so we were measuring the transit timing variations in the system. But on the left here, I've shown one night of a light curve from Palomar WIRC. And it's compared to 4 years of data on the same target with the Kepler Space Telescope. And they're plotted on the same y-axis. So you can see that we're really starting to get down to precisions that are quite good for doing light curves and planetary photometry. And in my first 2020 paper, I showed that this space-like near-infrared photometry is actually competitive with the Spitzer Space Telescope as well for stars that are fainter than a J magnitude of around 10 or so. And I'll mention that this work on Kepler 289 is in prep in an upcoming publication by my collaborator, Mike Grekluk-McKeon, so keep your eye out for that. But as this technique was sort of coming together, I was looking for applications where we could take this really precise system and use it for something unique to the near infrared. And then Jess Spake came to Caltech and gave a really great presentation at our group meeting and got me really excited about this line. So I ended up coming up with a system for precise narrowband photometry in the helium line to try to make these same sorts of measurements that had been made in 2018. So the system is not too complicated, and it leverages a lot of the infrastructure that we already had in place. It's not so dissimilar than to an iPhone camera, just with a few extra bells and whistles. So we take light from the telescope, we pass it through an optical element called a beam shaping diffuser. And all this is it spreads the light out into a stable top hat PSF with a diameter of 3 arc seconds. And that's done both to decrease the likelihood that the central few pixels saturate and mess up your photometry. And it also allows you to integrate for longer. So it just makes your CCD or your Mercatel, in this case, a better light collecting bucket. We then pass it through a narrowband helium filter, which I designed and commissioned in 2018, 2019. And then it goes on to form the image on the detector. And I'll talk about why the image looks so wonky with these rings in a second. But from here, we play the sort of normal game of aperture photometry. We place circular apertures around each source in the image. We count up all the flux inside those apertures, and we monitor those fluxes over time to construct light curves. I'll take a brief aside to just mention the helium filter. This is an actual physical picture of the helium filter, which I think is always fun to show. And it's designed for a center wavelength of 1083.3 nanometers in vacuum at a 7-degree angle of incidence, which I'll mention the importance of in a second. It has a full width half max of 0.6 nanometers, so it only lets light in at plus or minus 3 angstroms from the core of the helium line. This is simultaneously wide enough to accommodate any velocity shifts that we might expect in the system, but also narrow enough to know that we are specifically looking at the helium line and nothing else. And we also designed it to have a peak transmission of greater than 95%. This was a really important design consideration for us because our niche compared to the high resolution spectrographs is we wanted to make this measurement on planets and faint systems. So we really need to get all the photons we can through the instrumentation and the optics to really make those measurements precise. So back to this image, obviously when you go out and you look at the night sky, you don't see these ring patterns. So it definitely arises from our optics in some way. And it all has to do with the fact that for any filter, not just this narrowband filter, but for any filter, the bandpass of your filter will change as the angle of incidence that light takes through the filter changes as well. And in particular, for this optical setup, the filter wheel in WIRC is tilted by about 7 degrees from normal, which means that light encounters the filter at normal incidence all the way up here at what's called the filter 0 point. And as you move radially outward from that 0 point, the center wavelength of the filter decreases. So you can sort of think of it as a scanning spectrograph. As you move outward from this point, the wavelength that you're probing gets lower and lower and lower. And so what we're really looking at with these rings are telluric OH emission lines. And in fact, if you collapse this image radially around the 0 point, and you can construct kind of a pseudo spectrum of the sky, you'll note that the OH emission lines appear exactly where they're supposed to appear from, for instance, like literature catalogs from high resolution spectrographs. So with these kind of important design considerations in mind, I'll just briefly mention that at the start of each night of our observations, we observe a helium lamp, like an arc lamp, through the filter, just to make sure that we're placing our target on a region that we're sensitive to the helium line. And yeah, I think that's all I want to say about the calibrations. So with these calibrations in mind, we went out and took commissioning observations of the gas giant planet WASP-69b. And we chose this planet to measure because it had already been detected in the literature. So we wanted to make sure that we could recover the detection that was out there, just to ensure that we hadn't messed anything up in our observations. So at optical wavelengths, the planet WASP-69b blocks out less than 2% of its star's light. But our data are shown in gray. They're binned to 10-minute cadence in black, and our best fit model is shown in red here from the commissioning paper. We were able to use these observations to confirm helium in the presence of this planet's atmosphere at a confidence of about 10.1 sigma. And moreover, the amount of excess absorption that we saw, about 0.5% in our bandpass, corresponded exactly to what we would have expected if we took the previous observations from Carmenez and convolved it with our filter transmission profile. So all seemed well and good, and we were sort of convinced with these observations that we hadn't made any crucial errors in designing the experiment. So after designing this system to do photometry in the helium line, we wanted to take it a step further and actually conduct a survey of mass loss in the most favorable targets with Palomar WIRC. But before I go into describing that survey, I will again pause briefly and see if anyone has any quick questions. Yeah, Everett?
Yeah, I was wondering, this beam shaping diffuser seem really, like the precision's really good. I was wondering if the field is crowded, if you have the ability to like change the size of the beam so the stars are not overlapping.
Yeah, that's an awesome question. So for our particular setup, we can't. So the like opening angle of the diffuser is set by the pattern that's etched onto the surface of the optic. So unfortunately, if you want, like for the crowded fields, you're absolutely right. Like sometimes you don't want it to be 3 arc seconds. Maybe you want it to be like 1 or 2. You would need a different diffuser in the filter wheel. But I think there might be other telescopes that have multiple diffusers in their filter wheel. We just don't have that. It's turned out okay for all the fields that we've gone after, but it definitely could be a problem for other fields. Yeah.
Thank you.
Okay, if there are no more questions, I'll keep moving. So when constructing a survey to look at mass loss, or constructing a survey to look at anything, we want to first define the criteria for the planets that we should look at. And for our survey, we wanted to look at gas giant planets because these planets are large, they block out more of their star's light, and they give us bigger signals to work with. We wanted to look at low density gas giants, as these planets are the least adept at holding on to their atmospheres against the effects of photoevaporation. We wanted to look at bright systems. Everyone wants to look at bright systems because you get as many photons as you can to make these measurements. But I will say on the faint end, we can measure large outflows down to a J magnitude of about 12, which is, I think, about a magnitude or a magnitude and a half better than what spectrographs on what high resolution spectrographs on sort of 3.5 to 5 meter class telescopes can currently do. And that kind of speaks to the efficiency of the filter. And just because Palomar Observatory is in the northern hemisphere, we restricted ourselves to looking at northern targets, although I will mention there are a number of great southern targets that we just couldn't look at. And finally, we restricted ourselves to looking only at K-type host stars. This was pointed out in 2019 by Antonio Klopcic as the optimal stellar spectral type for populating the helium line. This is because they have kind of a good balance of extreme ultraviolet radiation, which ionizes ground state helium and it recombines from that ionized state into the metastable state. But they have relatively low levels of mid-UV flux, which directly ionize the metastable helium state. And in fact, it's for these reasons that most of the planets with measured helium absorption orbit K stars. And just to sort of connect back to the motivation for this work in the first place, the sample that we ended up selecting really traces the upper edge of the Neptune desert. So here I'm showing the mass period plane with one realization of the Neptune desert drawn with the dashed lines. It kind of depends on who you ask where that boundary falls. But our planets are shown in blue, and other planets that we could have observed, but other folks have already observed to high precision are shown in red. And as a reminder, the question that we're trying to answer is, was this region destroyed by mass loss, or was it never populated to begin with? Now, if these planets were destroyed, then we might expect planets on the edge of the Neptune desert to be marginally stable to photoevaporation. That is, if we picked out a sample on the edge of the Neptune desert, as we've done here, they should have relatively large present-day mass loss rates because they just narrowly avoided the fate of being destroyed by photoevaporation, if indeed that's the process that clears out this desert. With this goal in mind, we went out and measured the 7 planets in our sample. We detected mass loss for at least 3 of these planets. And I say at least because this is definitely still a work in prep. But sort of a menagerie of these light curves are shown on the right-hand side of this plot. And I'll point out that this one, HAT P18b, was published by my summer student, Kim Paragas, in 2021. And, I guess that's this year. And in this work, she took 2 transits of the gas giant planet HAT P18b and compared it to the light curve as observed by TESS in a near simultaneous epoch, and was able to confirm helium in the atmosphere of this planet at around 4 sigma confidence, which was really exciting. And it's the first time mass loss has been reported for this planet, which is quite faint, has a J magnitude of 10.8. And just to drive home what we can actually do with these light curves, we can use them to constrain the present day mass loss rates of these planets. So for those light curves of Kim's that I showed you in the last slide, we went ahead and did the exact same thing that had been done previously in Megan Mansfield's paper. So in each one of these grid cells, we constructed a one-dimensional isothermal Parker wind. We computed the helium signal that would correspond to that Parker wind and compared it to our data. And we can see that to pretty good confidence, the planet is not losing mass at a rate larger than a few times 10 to the 11 grams per second, which is pretty inconsequential for this planet's evolution. Now, we can quantify what I mean by that, by inconsequential for the planet's evolution. What we're interested in is the fractional mass loss that the planet has endured over its lifetime. So we can get that by taking the ratio of the current mass of the planet to its initial mass, which we get by taking our constraints and integrating them back in time, accounting for things like the time-varying XeV luminosity of the host star. And preliminarily, for all the planets in my sample, I find that they cannot have lost more than 1% of their initial masses by photoevaporation. What that suggests to me is that the upper boundary of the Neptune desert appears to be exceptionally stable to mass loss. And in turn, I think that that implies that the Neptune desert is at least the upper boundary of the Neptune desert, is a pristine tracer of giant planet formation and migration mechanisms. In other words, these planets haven't been altered that much by mass loss and related evolution. So when we see this boundary, it's probably telling us something about how the planets got there. Now, you may approach that conclusion with some healthy skepticism, especially because I mentioned we are integrating these constraints back in time, accounting for the time-varying stellar XeV luminosity, which is an inherently uncertain reconstruction. So one of the things that we can try to do is just measure mass loss for planets at early times. Unfortunately, we don't have many young planets, young transiting planets that we know of that we can make these measurements for. But there is one system called V1298 Tau that is kind of ideal, or so we thought, for these kinds of studies. It was discovered by Trevor David in 2019, and there are 3 planets in the system with known orbital periods. There's planet C at 8 days, planet D at 12 days, and planet B at 24 days. The inner 2 planets are around half a Jupiter radius in size, and the outer planet is around a Jupiter radius in size. And I'll also mention that the host star is a K-star, which is another reason why we should be optimistic to make these measurements for V1298 Tau. Oops. So we went out and made these measurements. And in a full transit observation of V1298 Tau C, we saw absolutely no signal, unfortunately. So what's plotted here is our light curve in gray binned to 10-minute cadence in black. And the best fit model is shown in solid blue. The transit at optical wavelengths, as observed by K2, is shown in the dashed lines. And so you can see that we definitely did not detect the transit here at all. Oh, and the red line is a realization of our GP systematics model. And yeah, when your systematics model is kind of on the same amplitude as the signal you're trying to detect, it's a good indication that you're not really detecting anything. So we didn't really see a signal, which was a little disappointing. We were expecting to see something of order 1%, but we can actually comfortably rule that out. And I think that is still an important conclusion because it might tell us that, I don't think it tells us that the planet's not losing mass at all. Instead, what I think is going on is this planet is so close to its host star that helium can't reside in the metastable state for too long. In fact, it should just get directly ionized out of that state because it's in the presence of such a large incident XeV flux. And this has implications for how mass loss proceeds at early times. It would imply, in particular, that this planet is experiencing a recombination limited outflow rather than an energy limited outflow. When we looked at V1298 Tau D, we think we observe a signal. And it looks repeatable over 2 nights of observation, which is really exciting. So here I've shown night 1 with the circles and night 2 with the triangles in this light curve. And the signal appears to be of consistent amplitude in both nights, which gives us some cause for celebration, I guess. But to stitch this light curve together, we needed to invoke a relatively large transit timing variation, a relatively large deviation from a Keplerian ephemeris, which may not be unexpected as this system is close to a chain of mean motion resonances. But it was enough for us to be wary of this conclusion and call it a tentative detection rather than a slam dunk. I did recently get another night on V1298 Tau D. We have another full night of observations on this system, and still processing the data, but hopefully we are able to confirm this in the near future. And finally, for V1298 Tau B, we also observed an egress of this planet, but got kind of an inconclusive result. As you can see, the light curve, we did detect kind of the solid body transit of the planet, but we didn't really need to invoke any excess absorption in the helium line to explain the data. And this actually might be because V1298 Tau B has a relatively high mass. There's a paper out maybe a week or two ago explaining that this planet may actually be relatively high density based on some intensive RV observations they've made of the system. So if you believe that, then the story all sort of holds together for Planet B. So now that I've talked about some of the observations I've worked on, I'll quickly switch gears and talk about some of the modeling work that I've done to improve outflow modeling using an energetics framework. So I've kind of skipped over this degeneracy that's been present in all of these 1D Parker wind model plots between the assumed mass loss rate in the Parker wind and the thermosphere temperature. This degeneracy can span orders of magnitude in the mass loss rate. So we'd really like to cut down on it in some way. And this is, by the way, the constraint for HAT P11B using data from Megan Mansfield's 2018 work. So the question that I wanted to ask is, do all of these outflows satisfy energy balance, or do only a subset of these outflows satisfy energy balance? And it seems like kind of a simplistic question to ask, but actually when you're constructing the Parker wind models, it's just assumed that the density structure is maintained via some mechanism. But in the case of these photoionized winds, we actually know what the energy source is. So we can go a step further and actually apply this, apply energy balance to these outflows and see which ones hold up and which ones don't. So the simplified picture of outflow energetics that most of us kind of use is called the energy limited mass loss rate, which is reproduced here. It's what I was alluding to before when I was talking about the direct proportionality between the mass loss rate and the incident XUV flux. All this really is a statement of it's a balance of the heating rate of the planet. The planet experiences an XUV flux of XUV. It's irradiated over an area pi r squared, and it's heated with efficiency epsilon. And that's balanced by the gravitational potential of the planet. Another way to look at it is if you multiply the denominator over, the heating balances the mechanical luminosity of the outflow. But this sort of proxy for the heating rate, we actually don't need to use for a photoionized Parker wind, because we can calculate how much heat the Parker wind generates from the photoionized Parker wind model. And in fact, we can just write down the expression for the heating rate, for the integrated heating rate, which is shown here, and equate it to the proxy that we've been using in the energy limited mass loss rate to get an upper bound on what the mass loss efficiency can be. And it's an upper bound because you can always balance a lower efficiency by including cooling, which I don't model in this work. So I went ahead and did this calculation, and I ended up with an expression for this maximum efficiency for an energy limited outflow, which I won't go too in detail into. Please feel free to ask me about it later. But the upshot of all of this is that not all Parker winds can sustain themselves. And if we apply the energetics framework to this picture for HAT P11B, only a small subset of Parker winds are self-consistent in an energetic sense and match the helium data. So the self-consistency calculation in this case told us that the outflow had to be relatively cool, and the helium data tell us that the outflow has to be relatively weak. And so with those two constraints combined, we can kind of get a sense for what this outflow is actually doing. And in gold here, I've plotted a 1D Parker wind retrieval on a different data set for the same planet. So this planet was also measured by the Carmenes spectrograph by Romain Ayart and collaborators. And they got a really precise line shape from which you can break the degeneracy anyway, because you kind of measure the temperature with the broadening of the line. And when they do that, their measurement agrees really, really well with our combined self-consistent region plus helium, unresolved helium observation shown here. Our results are also in good agreement with self-consistent one-dimensional models from Sals et al. That suggest that the outflow should be of order 10 to the 10.5 grams per second. So in this case, all of these methods, all these independent methods agree with each other and really demonstrate that what we have for HAT-P11b is an energy-limited outflow at around 10 to the 10.5 grams per second and a temperature of around 7,000 Kelvin. So that's kind of all I want to say with the outflow modeling, and I realize I'm running a little low on time here, so I'll just jump quickly into the future directions that I'm excited for. The first thing I'm excited for is for TESS. TESS is already up, but I think there's still a lot of work to do in characterizing the atmospheres of planets from TESS. And I think TESS is really going to revolutionize studies of planetary mass loss. So here I've plotted the Neptune desert in the period radius plane instead of the period mass plane. And I've delineated a proposed sample of planets between 4 and 8 Earth radii. So these are kind of smaller, lower mass planets than I was considering in my survey. And they might be more susceptible to mass loss for that reason. And I zoom into that region of the radius period plane here. 2 planets that live in this region are noted, HAT-P11b, which I've talked about extensively, which has a helium detection, and HAT-P26b, which I've actually measured as part of my survey sample. The rest of the planets that are noted on this plot are test candidates that orbit K-type stars that have passed initial vetting. And as you can see, there are a lot of really great test candidates for helium studies. In fact, many of them have higher predicted SNRs than HAT-P11b, which has already been so influential in building our understanding of how to interpret these observations. So the increase in sample size is something like a factor of 25. We've gone from 2 planets with very observable outflows to about 50. So when, in astronomy, when you get a factor of 25 increase in your sample size, I think something good is bound to happen. So I'm really excited to go out and measure mass loss in the atmospheres of some of these test planets. I've also, for most of this talk, been talking about mass loss in giant planet atmospheres. But mass loss can be important and can be even more important for smaller planets. For instance, sub-Neptunes and super-Earths. We think that the boundary between those 2 populations is delineated by mass loss in some respect, whether it's photoevaporation or something more akin to core-powered mass loss. But these planets tend not to have super strong signatures in the helium line, maybe just because they don't have that much helium to begin with. So I've been hunting for a little while for a tracer of high density or secondary atmospheric outflows that might be applicable to these sub-Neptune sized planets. And in this search, I've looked through some interesting corners of the literature. And one of these interesting fruitful avenues of exploration has been looking at the literature of lightning spectroscopy. So lightning, we have a great secondary atmosphere here on Earth. Lightning kind of simulates, what might happen when you have a large energy input into a secondary atmosphere. So we can look at the spectrum of lightning. And in fact, this has been done for many, many years. This is a paper from a long time ago when someone pointed a telescope at lightning on Kitt Peak, which I'm sure that the observatory staff was jazzed about. But I want to draw your attention to just one line in the spectrum at 811 nanometers, or 8100 angstroms on this plot. And this is a line of metastable argon. Now, argon is a really interesting species in the Earth's atmosphere. The majority of argon that we have is derived from the radioactive decay of potassium-40. So it's kind of this unambiguous indicator that our atmosphere is secondary. And I think that it's a really exciting potential tracer of outflows in the same way that metastable helium is, but for sub-Neptune and super-Earth-sized planets. So to demonstrate why I think it's so exciting, here's kind of the level diagram schematic for metastable helium. So we have the ground state down here, the metastable state up here. The way you make it is you ionize directly out of the ground state and you recombine it into the metastable state, which is radiatively decoupled from the ground state. And from here, you get the metastable helium line. The atomic structure for the argon atom is actually really similar. It's so similar, in fact, that I was able to just copy and paste this diagram over and change the energy level labels. So in the same way, you could ionize argon out of its ground state, populate this 1s5 state, and generate the metastable argon transition that way, if your planet is at just the right spectrum, or is being irradiated by just the right spectrum. So this is something that I'm really excited to look into as well as part of the future postdoc program. And it's something that I'm looking forward to. So with that, I will leave up this summary slide of what I've talked about, and I'm happy to take any questions. Thank you.
Okay, Vladimir has a question.
Yes. Hello, Shreyas. Thanks for very nice presentation. And I have one question and one comment. The question is that, so you observe those objects in helium-1, 10830, and have you tried to also complement those observations with Hubble Space Telescope of Lyman Alpha? So seeing if, as far as I understand, those mass loss rates identified in Lyman Alpha normally don't observed in helium-1 or vice versa. So can you please clarify this issue, which I'm not exactly aware?
Yeah, totally. So I think there's a couple of issues with the Lyman Alpha observation. Oh, sorry. I think there's like a little feedback. Do you mind muting real quick? Oh, maybe it's not. Okay, thank you. Yeah, so for the Lyman Alpha observations, the big issue is that the line core is suppressed by interstellar absorption. This affects your observations in two ways. One, you just can't observe Lyman Alpha absorption, planetary Lyman Alpha absorption for planets farther than around 100 parsecs away. That already removes a lot of planets that I've talked about from the sample that you could do Lyman Alpha with. The other thing is, because the core of the Lyman Alpha line is suppressed, you're only really tracing the high velocity tails. And these, by high velocities, I mean 100 kilometers per second or so. Whereas the helium line is tracing from like 0 to 10 kilometers per second, right where the wind is getting accelerated. Lyman Alpha is tracing kind of the region where the stellar wind and the planetary wind interact. So not to say that Lyman Alpha is like not useful, right? It's a super useful probe of this boundary between the stellar wind and the planetary wind. But they don't exactly give you the same information. And moreover, it's usually quite difficult to get both sets of observations for the same systems. There are, however, some attempts to do this in the literature by a group led by Lampon, I think, Lampon. So I would look into that if you're interested. But in general, I'm a little pessimistic about that.
Well, actually, the Lyman Alpha probes regions at temperature about 10,000 kelvins, while the helium-1 is about over 20,000, right? So that's basically different temperature regions. So we're talking about absolutely different regions probing by those two lines.
Yeah, I think the different regions thing is definitely true.
Yeah, and the second question is about, so you mentioned about the photoionization-driven outflows, but we know that all giant planets in our solar system, at least, and we understand the dynamo mechanism of the generation of magnetic fields, they should have magnetic fields. and especially for the star that you mentioned, V1298 Tauri. So this is a a pre-main sequence star, and it has a very strong stellar wind. And so the interaction of the stellar wind with magnetic field, as we know, generates a strong So the interaction with magnetosphere generates strong ionospheric currents and Joule heating. So it has been shown in a number of papers, for instance, Ofer Cohen in 2014 and 2018, that this outflow associated with the Joule heating can exceed the XUV ionization-driven mass outflow, simply because the electromechanical energy flux in the stellar wind can be greater, especially for those young stars, than the energy flux from extreme UV.
Sure, I think that's definitely true, and probably understudied, I would say, in the context of the exoplanets at least. But I think it is a little complicated because the stellar wind can also confine the outflow, because I think there's some group of simulations that show that if the stellar wind is really, really strong compared to the planetary wind, you kind of get the outflow is sort of shepherded by the stellar wind in that sense. And then also the planetary magnetic field can do that as well, because a lot of the material in the upper part of the atmosphere is going to be photoionized. So it's going to be coupled to these field lines, which may be closed, especially near equatorial latitudes. So I think I think there's like a lot of work to do when it comes to the problem of Joule heating, because I do think it's like pretty understudied for these outflows.
Yeah, I completely agree with you. So just want to mention that those papers that say that that talk about suppression, they don't take into account ohmic heating at all. So
yeah, that's true. That's true.
So it's just a half of the story. So
okay, thank you very much. I think you can continue after this talk if you have more questions. But can we move on to the next question before the end of the hour? Chun Liang is the next one.
Hello, that's great talk. I have several questions, but let's just start with the first one. So typically the planet mass and radius measurement has quite large error bars. So when you claim the planet near the desert boundary, you said the mass loss rate is not large enough to destroy the planet within lifetime. So is it possible we don't have accurate planet mass or a surface log G that place the planet very close to that desert boundary? Actually, is relatively far away.
Yeah, great question. So here, I think I should have been more clear. These planets are some of the best studied planets that we have, just because they're quite large and they're pretty close to their host stars. So the fractional uncertainty on their mass is oftentimes like less than 5%. So I think that's good enough to make these conclusions, even in the presence of like systematic errors in the masses.
Okay, so let me just ask another one. In your final future projects about the argon, so I noticed in your under level, the argon metastable to the ionization is 4 eV compared to the helium is 5 eV. So I think at the stellar black body, the 4 eV to 5 eV range, like 4 eV intensity is way stronger than 5 eV. So will it possible that the argon being metastable, argon being ionized very quickly and just destroy your metastable states?
That is a fantastic question. I'm definitely worried about that. It is just something that we're gonna have to calculate out. Like without the part of this project that I'm working on now is just getting the state resolved photoionization coefficients. So it could be that like these photons can photoionize this the out of the metastable state really efficiently. But like for instance, a different stellar spectrum other than like the sun's might be a little easier to work with. Like say, I don't know, if you have an M star spectrum, maybe that gives you a little less flux at 4 eV to work with. But it's just something where I'm gonna have to calculate out and see what it comes up with. but definitely something that's on my mind.
Okay, thank you.
Okay, the last question, Christopher.
Hello, thank you. Very, very nice talk. I was just wondering, you have lots of observations of V1298 Tau, presumably outside of any potential transit. It could even, I think, maybe come from a transit, but this line is thought of as a chromospheric line. And so chromospheres are variable, and they can be variable on relatively short time scales. So how much does just the stellar variability in this line potentially affect the signals you're looking for and the noise in those signals?
For sure, yeah. It definitely affects it a lot. On different time scales, it affects it in different ways. So simultaneous to this, we also undertook a measurement campaign with the Hobby Eberly telescope using the Habitable Planet Finder there. And so there were a couple of spectra separated by weeks and months. And you can clearly see in those spectra that, if you look at V1298 Tau today and then in a week, the amplitude of the absorption can change considerably. So it's pretty difficult then to try to stitch together observations across many epochs without running into that issue. On the short time scale side, the baseline that we were dealing with didn't look too, by the baseline, I mean the out of transit variability, didn't look too different to what we would have expected from pure photon noise, plus like a little bit of margin from the instrument. So there, I don't think that the short timescale variability in the line has affected these measurements too much. And from the Hobby Eberly telescope measurements, there were some of these we took like one after the other. So those seem to agree as well.
Right.
So on long time scales,
I would also be worried just, if the star has like plage regions on it, if the planet transits plage, even if it's a solid thing with no atmosphere, you would see variations in the helium line just from that.
Yeah, absolutely. It's something that we considered in the paper, and it's ultimately, I think photometry is probably a difficult technique to make work for the young system. If you can, I think that if we could get a spectrally resolved transit and we could actually see kind of the Doppler shadow of the helium line during the transit, I would feel personally much more confident with that. But I think this is motivation to go out and do that. But I agree.
Cool, thank you.
Okay, thank you. Any other question? All right, so then now let's thank Shreyas for his great talk. They're all on mute and thank you. If you have more questions, you can hang out a little longer. And otherwise, it was happy Thanksgiving. We'll see you next week.
Thanks so much. And